Welcome to our lesson on 8.2 called U Substitution. So 8.1, just as a reminder, was all about finding antiderivatives. So we learned about the constant rule, the power rule, the sum and difference rule, and those were three major rules that we utilized a lot for 8.1 and 8.1 extension. So here we are at 8.2 U Substitution. So this is going to bring us into a lot of the more in-depth functions and finding their antiderivatives or the integrals for particularly today composite functions. So U substitution is basically this procedure that we're going to use in order to do that. We're going to kind of, again, ease into things just like we did the other day with the other stuff. So the first thing I'm going to ask you to do is work on this warm-up, which is just finding the antiderivatives of simple things that we could use our constant rule, our power rule, and our sum and difference rule for. So you're going to work on this warm-up. And then I'm going to ask you to also do this just revisiting of the chain rule and finding derivatives. And then we'll come back and jump into how we're going to handle this U substitution. So you're going to pause the video and just work on that, the warm-up and this little section on revisiting the chain rule. So take a couple minutes to do that and then hit play when you're ready to come back. So pause the video now if you haven't paused already. Okay, welcome back. So here we are. You've spent a little bit of time, hopefully, and worked through these problems on your own, but let's just clarify and make sure we're all on the same page. So for this first one, find the following indefinite integrals, the integral of e to the x plus 3x to the 5 halves dx. So again, because of the sum and difference, we can kind of break up each of these and do the integral of this guy and then the integral of this guy and then just put them together. So the integral of the antiderivative of e to the x, we should know is just e to the x. Plus, and now this guy here, 3x 5 halves, this is a little bit more complicated. We've got a constant and then a power rule ready guy. So you can think of it as taking the 3 to the outside, that constant. And now we're going to use our rule. So 1 over 1 more than the power of 5 halves plus 1 is 7 halves. X to that same power, 7 halves. Yikes, a little big. And now we're just going to clean that up a little bit. So we're going to have e to the x plus. So let's just do this little bit here. So we have 3 times 1 over 7 halves. 1 over 7 halves we should quickly be able to know is 2 sevenths. 1 divided by 7 halves is the same as 1 times 2 over 7. So that's just going to be 6 sevenths x to the 7 halves. And again, that should work out there. If we needed to, we could rewrite it. So this is e to the x plus, since we're not allowed fractional or negative exponents, I'm going to make that 6 sevenths x, his power is 7, his root is 2, plus c. So that's my final answer there for that first warm-up. Yikes. All right, the second one here, a little bit easier in some ways. So we've got 5 cosecant squared of x. So right away the 5 can kind of hang out. And then you're just really thinking of cosecant squared and who's his antiderivative. So his antiderivative is the cotangent, right? Cotangent's derivative is negative cosecant squared. So since this is not negative, that means that this original guy must have been negative. So negative 5 cotangent x. And then plus 3. And who's the antiderivative of secant squared, meaning who has a derivative that's secant squared? That's going to be tangent of x. And then plus c again for that constant idea. So this is a negative out front. So one more time, since cotangent's derivative is negative cosecant squared, but this guy here is positive, that means the original must have been negative, so we've got a negative there. Brunk. So there's my final answer for that guy. Okay, so today we're talking about composite functions. So again, this is a lot of words. That being said, a function like this is a composite function where you have x cubed plus 4x minus 7 all raised to the 5th power means this function here, this polynomial, is then being raised to the 5th power. It's a polynomial inside of another function. And so that's a composite function whenever you put one function inside of the other. So when we took the derivative of guys like this, like down here on, let's revisit the chain rule idea, sine of 3x, we would always say, oh, sine of u, right? Sine of u was always cosine of u, so it was cosine of the thing, times, then we always had to account for that inside and say the derivative of the inside, which is 3. So we would clean that up and get 3 cosine of 3x. So that should be familiar to us. Same here on the second one. So the function inside our u is 2x plus 1. So it's really u to the 7th. So 2x plus 1 is our inside function, and the whole thing to the 7th is the outside. So when we did the chain rule there, we would do a little 7 times the original to the 1 less power times, again, the idea of that inside piece, the derivative of the inside, which was 2. We would clean that up and come up with 14 times 2x plus 1 to the 6th. All right, on to the next one, same idea. So we have the function x squared, there's our u, inside of e to the, right, e to the u. So e to the u, our rule was e to the u's derivative is e to the u, so it was the same thing, times the derivative of the u, so that's again that top bit, which was 2x. And again, we would clean that up as 2xe to the x squared. So that should all be familiar to us. So in the same mindset, now that we're talking about integrals, we're talking about going backwards. So here's this all written just in integral notation, meaning if the derivative of 3 to the x is cosine of 3x times 3, then the antiderivative, or the integral of cosine of 3x times 3, is sine of 3x plus c. So this is going forward with derivative. This symbol tells us to go backwards, right? Find the guy who had that derivative. So similar, since this guy's derivative is this, then his antiderivative is 2x plus 1 to the 7th. So finding the original. So again, this is just this bottom section here is just a repeat and a relationship clarification of what was going on up here. Okay, so we should be ready to move on. So here is going to be our first example on U substitution. So I'm going to ask you again, as usual, right? This is going to be a doozy. It's the first time ever that we're doing this. So we're going to kind of try to understand the procedure. It is very much a procedure that we will get used to the more we do it. But obviously this first time through, it's going to be a little bit fuzzy and need a little bit of slow explaining. So here's the first idea. So just again, we talked about U substitution. So U substitution is a process we're going to use whenever we see a problem that looks like it's a chain rule type of problem, meaning that there's a function inside of another function. So if you look at this first problem right away, you should zoom out and be able to see, oh, this is a cosine function. But when you look at the cosine on the inside, it's not just an x, which is what we were dealing with in 8.1. It's now an x squared. So that changes the game right there, because now it makes us have to consider that inside piece and what could be happening. So the first thing we do is we define our u. So we figure out what u is. So u is always the thing that was inside. So again, if I scroll back here for a second, you can see the u on these sections here. The u here was 3x, right? The thing inside of the sign. The u here was 2x plus 1, the thing inside of the thing to the 7th power. The u here was x squared, the thing inside. So it's always the thing kind of inside the other function. So in this case, it looks like u is x squared. X squared is the function inside of the cosine. Again, don't worry about the rest of it just yet. You just want to figure out what u is. Your next step is to differentiate u to find du. Now, when you take the derivative of something, technically, you need to be able to include dx at the back. So when you take the derivative of u, so x squared, that's simple enough, it's 2x. Then we're going to add on this dx at the back, dx. Then what we want to do is solve for the dx. So I should have maybe made that a little smaller. I'm just going to rewrite that quick. So du is 2x dx. So we have the derivative of this guy, x squared, is 2x. And then you always want to tag on that dx. So that's something that like we weren't always doing because it's like a little bit formal as far as language goes. But that's something you really have to get into the habit of doing here. Then we're going to solve for dx. So dx is this guy right here. So we just want to solve for him. So if we're solving for him, we're going to divide by 2x. We get dx equals du over 2x. Okay. We're now going to substitute, step 3. Substitute into the integrand and simplify. So we're going to take this original guy up here and basically just rewrite him, substituting in u's and du's and all that kind of stuff. So that's the integral. Cosine. Instead of x squared, we've now called that u. The 2x can kind of hang out for now because we don't have anything else to rewrite that as. But dx, we do have something. Dx, we said, equals du over 2x. So that's coming right from here. So one more time, this is the key step, step 3. You are taking this literal problem that we started with, and you are rewriting every piece of it. So I'm going to draw all over the picture for a second here. I'll use yellow. So the integral, cosine, cosine. X squared, this is where the change happens. X squared becomes u. 2x sticks around. And then dx we write as du over 2x. And again, that's coming from step 2. We just solved for dx. So we knew that dx equaled du over 2x. We just replace it with that value. Okay, on to the next. 4, check that your expression only includes the variable u. So it does only include the variable u, except if x still occurs anywhere in the integrand, take your definition of u from step 1, solve for x in terms of u, substitute, blah, blah, blah. Basically, this is saying that we need to get rid of anything that's not a u. So if there's something that's not a u, so if you look in step 3, there are things that are not u's. We have a 2x here. I don't like that color. Let's change that. We have a 2x here, and we have a 2x here. Well, we have two 2x's, which is not good. We don't want anything with a non-u in it. But since there are 2 of them, guess what I can do? If you said cancel, then you're right. So we can cancel those 2x's. Since one is on the top and one is on the bottom, right? This is being multiplied, this last bit, du over 2x. He's in the denominator, so he can cancel with that 2x. So now we really just have left cosine of u du. Now we go back to what we did last week with 8.1, and we say to ourselves, what is the integral of cosine of u? So you integrate, and you treat u just like you would an x. So what is the antiderivative of cosine of u, meaning who has cosine as his derivative? That would be sine of u. And then, of course, we're going to say plus c. So, again, big idea. Took out this little u bit, rewrote it so that it had only the u's, canceled what we could. If you still have x's left, again, you'll know you're in some trouble in this step. If you have a constant left, that's okay because a constant can just be moved to the side. For now, we're going to, hopefully, again, see some simple repeating procedures. Here we have cosine u du. We got it down to that. We say to ourselves now, okay, who's the antiderivative of cosine u? That's sine of u plus c. Substitute back for u. I'm on step 6 now. Substitute back for u. So whatever the u was, we put back in. So if you remember, u was x squared and then plus c. And then again, this is the beauty of this section, is that now we can always check back. So we're just going to check back by saying to ourselves, okay, that is our answer. Let's take the derivative, though. The derivative of sine of x squared is cosine of x squared times the derivative of the inside, which would be 2x. And then you're checking yourself. Is that what we had to start with? And the answer is yes. Yay! Okay, so going through that first U sub example is always a little tough. But once you get the hang of it, you're going to see it's actually not that bad at all. So here we go. Let's jump right into this next one. So we'll change over a new color. So example 1. So we're going to follow those steps. So we're going to keep these steps really close. I'm going to keep them in eyesight. The steps are going to be key, especially for the first few, just getting used to this idea of U sub. So here we go. The first step, if you remember, was to pick out what U is. So I'm going to do that over here. So U, in this case, again, very similar to the last problem, is the thing inside the function. So since it's cosine of something, and that something is not just an x, we're going to call that our u. So u here is x squared. And when I say call that, that's one of the things just to bring up now. You're not in charge of determining what it is. It's already determined. You're just picking it out. So you shouldn't be making that more confusing than it needs to be. Whatever the thing is inside of the other function, that's going to be your u. The next step, so that was defining u, check. 2, differentiate u and be sure to include a dx, and then we're going to solve for dx. So du would be the derivative of x squared, which is, again, similar to what we did before. 2x, we're sure to include a dx at the back. Then we're going to solve for that dx. So if we solve for dx, we're going to divide by 2x. So dx equals du over 2x. So again, similar to the last example, little differences will make all the difference when we're getting to know what we're doing here. Next step, I substitute into the integrand and simplify. So I take this original over here on the left, and I'm going to rewrite it. So integral cosine, instead of x squared, I'm going to call it u. 6x sticks around. There's nothing to rewrite that for. And then dx is the other thing that I'm going to rewrite for. So dx is just, that's coming from over here, du over 2x. So again, this middle step number 3 is where I'm taking the function and rewriting it. Sorry, not the function, the integral. And rewriting it. So I have the integral, cosine is here, x squared becomes u, 6x stays, and dx becomes du over 2x. Now is when I want to check that I have only u's in my expression. That's not the case right now. I have cosine of u, but then I have a 6x, and I have a du over 2x. So hopefully you're seeing, again, similar to the last time, we have these two things, which we're going to look to cancel. So in this case, we can cancel them. The 6x and the 2x are going to cancel, and it's going to become a 3. So I can just have a 3 there. Now that's where it's a little bit different. So since I'm going to want to integrate this next, we can do this in 2 steps if you want. We technically have a cosine of u times 3. So I'm going to call that 3 cosine of u du. In the future, I'm probably not going to bother with this step at all, because we should also realize that if you have a constant, you can just send that to the outside right away. So I send that to the outside of the integral. And then I just really have cosine of u du, which is where we were before. So then I'm saying to myself, once I get it down to just u's and du's, so that's a check mark now on step 4. Canceled these guys out here, 6x and 2x. Got it down to just u's and du's. Again, a constant is okay. We just move him to the outside because that's our constant rule. The 3 hangs around, and now I just figure out what's the antiderivative of cosine of u, meaning who has the derivative cosine of u, and that's sine of u. And again, plus c. So the only difference here is now I'm going to replace back. So that was step 5. I integrated. Now in step 6, I'm going to substitute back for u. So I have 3 sine in place of u. I'm going to put that x squared back plus c. There is my answer. And again, I like a check. So the benefit is that you can check yourself here. So if we had 3 sine of x squared plus c and we tried to find the derivative of it, right? So if this was our function and we were trying to find the derivative, we would say, oh, there's a 3. That's okay. He can just hang out. Sine of something becomes cosine of that thing times the derivative of the thing, which is 2x. Watch what happens. What would we do with this 2x? We would multiply it with a 3, which would make it 6x cosine of x squared. And is that what we started with up top? Cosine of x squared times 6x is the same as 6x cosine of x squared. Again, the plus c, just for the record, the derivative of a constant is 0, which is why he doesn't really change our answer. All right, practice makes better. Who's ready for another one? I feel like I can hear you screaming, yes, I'm ready. Here we go. Good. Example 2. Similar idea. Notice there hasn't been a big change in our lives. We're now just talking about cosine instead of, oh no, we had cosine before. Good morning. Different function though. Inside, different inner function. Not a big deal. Ready? Here we go. So first I'm going to draw a little line here just to separate myself. So first step, what's u and what's du? So what's our u in this case? It's the inner function. So that's going to be x cubed. What's du? When we find du, we want to make sure that we find du normally like we would with an x, but we want to add on that dx at the end. So u is 3x squared. Sorry, u is x cubed. Oopsies. Du is 3x squared. dx. Who knows the next step? We're going to solve for dx. So dx equals, do you hear the music in the background? Du over 3x squared. Okay, so you do all this side work before you even come over here to where the integral is, right? So we do u, find du, make sure to include the dx, solve for dx, and now we're going to come back over and substitute. So now I'm going to go here, integral, cosine, x cubed, we're now calling u, The 3x squared hangs out for a little while. And then dx we're going to replace with du over 3x squared. We get it down to just u's and du's. This guy's okay. This guy's okay. Not okay. This guy's okay. Not okay. But the 3x squared, guess what happens? Bye-bye. Those are gone. So now I'm down to cosine of u du. So now again, I'm saying to myself, who has a derivative that's cosine of u? And the answer is sine of u plus c. But then we're going to go back and replace. So we're not done. If our answer still has u's in it, we have to go back and replace. So what is our u? Our u was the thing from the beginning. So sine of u was x cubed plus c. Still worth the check. Let's see. Next around that. So if y is sine of x cubed plus c, what would y prime be? We're hoping we get what we started with, right? Because this is all about going backwards. So the sine of something becomes the cosine of something times the derivative of that thing, which would be 3x squared plus the derivative constant is 0. So I'm just going to put that there. And then would this all clean up to be cosine of x cubed times 3x squared? Is that what we started with up here? Yes. Hooray. So that worked. Okay, ready for another one? Here we go. Let's first start with u. So notice we're not in a trig world anymore. And again, each of these is a little bit different, but the same concept over and over and over again. Okay, so we're looking for the innermost function. So if you have 3t squared times t cubed plus 4 to the 5th, again, on the trig functions, it was like the guy in the parentheses. On these guys, same idea. If you see parentheses with a power up top, the guy inside the parentheses is your u. So our u in this case is going to be t cubed plus 4. So you should know now. We're going to go and find du. Then we're going to go and solve for dx. Why don't you do that? So you can hit pause and do that first. Find your du and then solve for dx. Don't forget to include a dx. And then you can come back. So go ahead and hit pause now. Okay, so here we go. Hopefully you tried that out, because it's no fun if you don't try it out. The derivative of u, so that would be 3t squared, and then plus 4 wouldn't have anything, but we're going to call that d, in this case, t. Since the variable is t, the derivative with respect to t was taken, so we're going to call that dt. Now we're just going to solve for dt, so dt would be equal to du over 3t squared. So hopefully that wasn't too bad. Next step, check back on your list. Next step is to rewrite the original. So we go back to this OG integral. The 3t squared hangs out for a little bit. This t cubed plus 4 is what we called u to the 5th. dt we just solved for, so that's du over 3t squared. Okay, again, a little different than the sines and cosines and the trig functions, but we can handle it. We're going to look to get this down to just u's and du's. So far, we have a little bit more going on than we'd like, right? So what is it? Well, there's this guy up front, 3t squared. Oh, wait, he's got a buddy in the back. Brunk, brunk, bye-bye. So those are gone right away. So again, you're kind of always going to look to this guy that you solved for, right? And whatever the denominator is here, you're basically going to look for that to cancel. If it doesn't cancel completely and it's constant, then that's okay. Because again, if there was a 2 left in the denominator, we should know that that's 1/2. If there was a 5 left in the denominator, we should know that's 1/5. But right now they're just canceling, which is nice. Or we saw the example before where you were left with a constant completely. I'm going to rewrite this as u to the 5th du. So I got it down to just u's and du's. And now I'm going to follow my derivative rules. I should say anti-derivative rules. So treat it like an x. If this was x to the 5th, what would be the derivative? I said derivative again. It's antiderivative. It's very late. It would be 1 over 1 more than the power, which is 6, u to that same power plus c. It would be that easy, right? So again, if this was x to the 5th, the antiderivative would be 1 over 6 x to the 6th. Since it's a u, we treat it just like an x. So u to the 5th becomes 1 over 6 u to the 6th plus c. And then again, I'm just going to replace So I have 1/6. What's our u? Our u was t cubed plus 4 to the 6th plus c. So that should be our final answer there. But again, I love a good check, so I'm going to zoom in really tight over here. So for my check, I'm pretending that this original was the guy that I just said is the antiderivative, right? So y prime equals, I'm pretending to take the derivative of my answer, which should give me the original I started off with because we're all going backwards here. Okay, so if I was taking the derivative of this thing, I should say, ooh, that's a chain rule. So I'm going to do 1/6 times 6, which is 1, times the thing to the 1 less power 5, times the derivative of the inside, which would be 3t squared, and again, plus that constant, but his derivative would be 0, so we don't need to care about him. Is this what we started with? Let's see, the original here, so I'm checking again this with this. Is this the same as this original here? Well, the 1 and the 3t squared would just be multiplied to become 3t squared. That's what we have. Times t cubed plus 4 to the 5th. Yay! So again, we got a good check there. So that's nice. All right. We're ready for 2 more? Ooh. All right. I'm going to pause the video for now. And I want you to try the next one, example 4. I feel like you can get through it. So pause the video and try to see what you can do with that one. All right, hopefully that didn't go too poorly for you and you had a fun experience with example 4. So welcome back. Again, I'm going to start to go a little bit quicker. If you're having trouble, we can always figure that out later. But at this point, it is kind of this procedure. So I find u, I find du. U, the guy inside, 3x plus 1. Du, his derivative. So his derivative here, this is a weird one, is just 3, right? Don't forget that dx. Solve for dx. Rewrite. So again, don't forget about these rules. Define u. Find the derivative of u. Solve for dx. Substitute. That's what we're up to. So we're substituting now. So integral 12 is just a number that's going to hang out. 3x plus 1 is what I called u. And dx we just solved for is du over 3. I look to cancel until I'm left with just u's and du's. So I notice I have a 3 and a 12. This 3 will cancel 3 into 3 once, 3 into 12 4 times. Remember we talked about this before. We had one like this. The 4, since it's a constant, will actually come out to the side. So I have 4 out here. U cubed du. Gosh, this is fun. Now I'm going to go to take the antiderivative. So again, this constant can hang out, 4. Let's do it. So u to the 3rd is just like an x to the 3rd. So it's 1 over 1 more than the power, that's 4, x, or in this case u, to the 4th plus c. We're going to clean that up a little bit. 4 times a 4th is just 1. So I really just have u to the 4th plus c. Got to replace that u. Can't leave him hanging there. So this is really 3x plus 1 quantity to the 4th plus c. Fun, fun, fun. Guess what I'm going to do? Check, check, check. So I'll do the check here. Check. So if y was 3x plus 1 to the 4th plus c, zoom in a little bit there, would I have gotten that other guy? Let's see. If I took the derivative of y prime equals, I would do 4 times the thing to the 1 less power times the derivative of the inside, which is 3, plus, again, 0. So this would clean up to be 12 times 3x plus 1 to the 3rd. That's what we started with. Yay! It works, it works, it works, it works. So our final answer was that. Okay, guys, I think we can do it. Power through. So this one's got a little twist on it. We can already see, right? Take a look at that one. First things first, what am I going to do? going to set up my U. So U here is the thing inside. So again, if you're looking at this going, oh my gosh, there's so much going on. Yeah, there's a little bit going on. The first thing you might want to do in this case, just because I find it easier, since we don't know a quotient rule, is rewrite this. So we should all be agreeing that this is the same as 2x times x squared plus 2 to the negative 4 dx. So that should be pretty easy to understand. I took that function down on the bottom, parentheses with the power, and moved it up to the top. Since it was in the bottom, it must be to the negative 4. So that makes it a little bit clearer, maybe, I hope, what your U is. You kind of always, again, look for the parentheses, and that's kind of a hint. Not always going to work out that way, but a lot of times it will. So U here is x squared plus 2. Going to jump right into du. So go ahead and do that now. Find du. Make sure you use that dx at the end and solve for dx. So hopefully you have something that looks like that for dx. I'm going to rewrite the integral. 2x. This guy is now u to the negative 4. dx, in place of that, I'm writing it as 2u du, sorry, over 2x. Tired. I want only u's and du's left. But again, kind of always look over in this spot. This guy's the guy who's usually going to be the one who's going to go away. See everybody who he can cancel with? Yes, he does. So the 2x and the 2x can cancel. So I have the integral, yikes, u to the negative 4 du. We can handle this, just a negative power. Nothing too crazy. Here we go. So we're going to use the power rule. So 1 over 1 more than the power. Be careful. 1 more than negative 4 is actually negative 3. U to that same power plus c. We're pretty much done. So this is just negative 1/3 u, which was x squared plus 2 to the negative 3 plus c. Almost done. No negative or fractional exponents. Good morning. So negative 1/3, I'm going to put the negative over here. Negative 1/3, I'll put a 1 here. I'll put the 3 on the bottom. We're playing that game, right? Who goes where? The 1 goes up top, the 3 goes in the bottom. X squared plus 2, if he's to the negative 3, where does he go? He gets sent to the bottom. And he becomes a positive 3. Oh, goodness, I can't fit it. Can I fit it? Can I fit it? Plus c. There he is. See him? So my final answer. How are we feeling? Fantastic? I have a little bit of room. I can't not show you the check. I can't not do it. Check. If our original function had been 1 over 3 x squared plus 2 to the 3rd plus c. Again, am I going to get the... Uh-oh, which way should I go? This way? Yep. Am I going to get that as my derivative? Well, let's find out. Here we go. In order to find the derivative, the first thing I would do is want to get this power rule ready, right? Or chain rule ready even. So we should agree that this is the same as negative 1/3 x squared plus 2 to the negative 3 plus c. And some of you may be saying, oh, I would use the quotient rule. Okay, that's fine. You have a chain and a quotient here. Or if we move this x squared plus 2 up, then we just have a simple chain. So that's why I'm doing it this way. Y prime equals... We would then take the negative 1/3 times the negative 3. Negative 1/3 times negative 3 is just a positive 1 times the thing to the 1 less power times, here's the trick, right, again, the derivative of the inside, which is 2x. Clean this up. So I would have 2x on top over, I would move this guy to the bottom, x squared plus 2, positive 4. So the 2x and the 1 out in front become a 2x, and they just stay up top. And then this x squared plus 2 to the negative 4 gets moved to the bottom. Is that the same as I started with? Yes, it is. Hooray. Good gravy. That was fun. All right. So that was U substitution. Oh, my goodness. That was fun. Yeah, lots of examples. Oh, I was just sorry. Lots of examples there. to all with a little bit of a different spin on them. When we go to do the problem set, that's going to, where you're going to start to see little changes here and there, but a lot of them, it's the same process. So I urge you, please go back to this first example. It really does, if you understand this first one and go through each example, that's the only way you're going to get this. There's no way to skip over this understanding and go, oh yeah, I can wing this. You really need to go back and understand the first one. If you understand the first, you move on to the second, move on to the third, move on to the fourth. Every little one has a little twist to it, and you've really got to put in the energy to make sense of it. So I hope, again, it will make sense if you keep practicing, and practice makes better, and really commit to the understanding. So that's it for now on U Substitution. Thanks for listening.